We're very happy to welcome Sam Hadden here today. Sam is a 5-year member at the Canadian Institute for Theoretical Astrophysics. He is kind of a local. I mean, I'm a little bit embarrassed to say this, but he was an undergraduate over at Purdue. Sorry, Sam. And then he did his graduate work at Northwestern with Yoram Lithwick, I think. Did a postdoc at CFA and then wound up at Toronto. And today he's going to tell us about loosely bound planets.
Yeah. Okay. Is my mic working? Okay. Sounds like it. Great. Okay. Yeah. So I'll be talking about something I've been getting excited about lately with the Roman mission coming up. And that is an opportunity to really probe the outer regions of planetary systems in a way we haven't been able to date. And my goal is to hopefully convince you that applying sort of the theory of orbital mechanics or dynamics can let us go beyond the sort of basic demographic data that we'll be getting from this mission and really say something about how planetary systems evolve over time and form at sort of solar system scales, and put our solar system in context as well. But to start, so over the past couple decades, exoplanet observations have revealed a very broad diversity of planetary systems. This is easy enough to appreciate by just looking at the sort of vast range of parameter space occupied by exoplanet discoveries in this plane of planet mass versus orbital separation. We find planets sort of scattered all over this plane, very frequently in places where we have no analogs in our own solar system, and a lot of effort in the field of exoplanets has gone into understanding how these sorts of planets form and evolve, and what went different in these systems that didn't happen in our solar system. But today, I'm going to focus mainly on how this parameter space, or what this plot looks like, is going to change in the next, say, 5 or 10 years, and how we can lay the sort of theoretical foundation or groundwork to make sense of those upcoming observations. Okay, there's sort of a conspicuous absence in this plot of planet discoveries in the parameter regions occupied by our own solar system planets. There's basically few, if any, analogs of our solar system planets, maybe with the exception of Jupiter, that have been discovered to date. And so you might look at this and fret, insofar as you're invested in other solar system planets being out there, that maybe we live in some sort of cosmic oddity of a planetary system, and solar system-like planets are rare. However, many of you have probably guessed already that what we see in this plane is influenced to a great degree by what we're able to detect. And in particular, the predominant exoplanet detection methods to date, namely the transit method and the radial velocity method, really struggle as you go to both lower planet masses and wider orbital separations. And they struggle to the degree that we're basically blind to any solar system analog, or have been to date, blind to analogs of our solar system planets, again, with the exception of maybe Jupiter. Okay. However, like I said, that is changing now and will change dramatically with upcoming microlensing observations by Roman. So my plan for the talk is to first tell you about how we can probe other exoplanetary systems at sort of solar system scales with the microlensing method. I'll give a little bit of a review of how microlensing works. And then I'll tell you how we can go beyond just the basic demographic information we're going to get from microlensing surveys by applying dynamics theory and using the fact that microlensing surveys also detect free-floating planets, so planets unbound from any star. And then I'll conclude by talking about some implications of the sort of dynamics that produces free-floating planets for entire planetary systems, not just the outer regions of planetary systems, and also some implications for our own solar system as well. OK, so let's get started by talking about what is microlensing and what can we learn. So microlensing has sort of been the black sheep of exoplanet detection methods to date, so it's worth going over in a bit of detail how it works. The basic idea is that you stare at some background field of stars, and as you do so, every once in a while you get lucky and some foreground star will pass very close to your line of sight to that background star, and when it does so, its gravitational bending of the space around it causes it to act like a lens, a gravitational lens, and as it passes along your line of sight, it magnifies this background source star, and you get these sort of characteristic brightening curves versus time that you see in this animation. Now, if in addition that foreground star has a planet orbiting around it, that planet's own warping of space can modify the properties of the lens in such a way that you get a little perturbation on this brightening curve indicated in this animation by the little bump that you see on the right of this. OK, that's a slick animation. What does this actually look like in real data? So I'm taking an example here from a recent paper by Zhang and collaborators showing microlensing light curve observed with the KMT network of telescopes. So on the left, you see this sort of month-long or months timescale brightening curve. So this is just the brightness of some star versus time. And then if you zoom in on the right side of this brightening curve, you see this little tiny blip here. If you zoom in, so that inset shows sort of zoomed in on that, you see on the time scale of a few days, there's this magnification event. And from modeling this light curve, you can back out the planet mass and orbital separation based on the time difference between the peak of the main stellar brightening event and the planetary event and the relative magnifications. This encodes information about the planet mass and orbital separation. OK, so ground-based microlensing surveys have been going on for multiple years now, and we're starting to get an emerging picture of what is out there around other stars at sort of the 1 to 10 to AU range. So this is recent results, again, from this study by Zhang and collaborators. And they find, based on 63 microlensing planet detections, that small sort of Neptune-scale planets are about a factor of 10 at least more common than Jupiter-sized planets around stars in our galaxy. So here they show the cyan here shows their number counts of raw detections, and if you turn the sort of statistical crank to figure out what that implies for the intrinsic rate of planets, you recover what's shown here in the blue points with error bars. So they infer about 1 in 3 stars. This is plotted in the number of planets per star. So about 1 in 3 stars hosts a Neptune-ish sized planet. And then Jupiter-mass planets occur around less than 1 in 10 stars. And this is corroborated by long-term radial velocity surveys as well. So it's good to see. Yes?
Can you say something about this, I guess, selection bias here? So there's the brightness of the background star, right, which you have to have some brightness. And there's the mass of the planet, which is your magnification.
Yeah, so the sensitivity to mass is set in part by how the cadence of your observations. So you can see, a little bit of how the sensitivity works by just how they've gone from the raw detections to the intrinsic rates. So you're less sensitive to, as in just about every detection method, you're less sensitive to less massive planets. And I'll show, So I'll show in a little bit also sort of what a sensitivity curve looks like in mass versus separation for Roman, but similar picture for other microlensing surveys.
The separation or the orbit,
Mm-hmm.
you can only determine that statistically, right?
That's right. Yeah. So you get a projected separation, and I had a slide that It's actually, sometime from the light curve alone, it's even worse than that. What you really measure is the planet-to-star mass ratio and the projected separation in Einstein angular radii, which you can turn into physical quantities if you detect the host lensing star. You figure out what star that is, you know the mass of the host, and so you get the mass of the planet. And if you know where it is in the galaxy, you work out what its angular Einstein radius is in physical units. Or for other things, you can sort of do, and I think that's actually what they did here, some sort of statistical analysis based on what's, a half solar mass star roughly is the most probable host for anything in our galaxy. As you go to lower stellar masses, stars become much more abundant. And you can fold in things like, I didn't see any host lens flux, so it has to be some star below some threshold. So there's, different ways. And there's also, on top of that, there's also sort of higher order effects in the light curve that sometimes let you break some of the usual degeneracies. But at the end of the day, a lot of what you get out of microlensing is, in fact, a sort of statistical picture.
How do you deal with the fact that, you can imagine as going across the star, the alignment of the planet might not be the same as the star relatively, right? So the magnification, is it that the background star that's being lensed is always presumed to be a disk, basically, and so if it's magnified, does it matter? Or
the fact that the background star is a disk. So if
they're in a line as it's going across, the alignment doesn't matter. Right?
Yeah. So it doesn't really matter where the planet is along the ring. What matters is what sets what you see is how you can work in a frame where, let's say, put the planet and star on the x-axis, and then you have a free parameter related to the angle at which the trajectory intersects the lens sort of setup. And you get different light curves based on what happens, or exactly how that happens. And it is a somewhat tricky inverse problem to solve, but people sort of know how to do it decently well, at least. Yeah. Okay. Okay, so we're already getting a picture from ground-based microlensing surveys. And this picture will be getting very much clearer very soon with Roman launching either next year or early 2027. So this is a wide field near IR space telescope. And as part of NASA's Roman mission, Roman will be carrying out what's called the Galactic Bulge Time Domain Survey, which is basically what it sounds like. It's going to stare towards the galactic bulge and monitor 7 fields there at a 15-minute cadence for 6 72-day seasons. And while it's doing that, it'll find microlensing signals in this dense background field of stars. Okay, so here's an answer to your question about what does the selection function look like. So this is the sort of sensitivity contours of what Roman is capable of finding. This is from a study by Matt Pinney and collaborators. And the contours are showing the number of planets one would detect in a logarithmic bin if every single star had a planet there. So that gives you a sense of how sensitive you are to different planets. And you can see that Roman is uniquely capable of finding planets between about 1 and 10 AU away from their star in a regime, and down to masses as low as a Mars mass or even less. And this is a regime that we've been totally blind to, as you can see, where current detections fall to date. If you take what we understand about planet occurrence rates based on what we've found to date and do some extrapolation, it's expected that Roman should find a few thousand planets, but we don't really know until we do the survey because, again, this is a parameter space that's totally unexplored. And like I mentioned earlier, so we'll get this great demographic data, but microlensing by itself is a sort of blunt instrument in the sense that you get a sort of point estimate of a planet's mass and its projected orbital separation. And there's little, if anything, you can ever do to follow up the planets that you find via microlensing and learn more about, say, their orbits or something. But as I'll argue, we can go beyond just this basic demographic information by leveraging the fact that in addition to finding bound planets, microlensing can find free-floating planets as well. And so, yeah, like I said, so microlensing can find free-floating planets or planets unbound from any star, any host star. The way this works is even simpler than finding bound planets. Just like the star in the animation I showed before can produce a microlensing signal, anything with mass is capable of lensing a background star. And so here you don't have to worry about two lenses, it's just a single lens. Of course, we don't observe cartoon planets floating through space. What you get when you observe a microlensing event, the main physical or main observable quantity that you have to connect to physical properties of the lens is the timescale over which the lensing occurs. And so this is degenerate with some other properties of the lens, like its separation and relative velocity to the background source star. But if you plug in reasonable numbers based on what we know about the kinematics of our galaxy, you find that planetary mass lenses have characteristic timescales on the order of hours. And so if you see a lensing event that lasts on the order of hours, it basically has to be coming from planetary mass lenses. And indeed, ground-based surveys already find these sort of short timescale events. So I'm showing a lineup of a few of these types of events found by the Ogle survey, just to give you a sense of what the data looks like in practice. Okay, and ground-based surveys, as I mentioned earlier, have been running for a while and accumulating these sorts of events. So this is a histogram of the event timescales found by the MOAA ground-based microlensing survey. You see this sort of log normal looking peak that peaks around on the order of a month timescale. And this is easily attributed to what we understand about the population of stars and brown dwarfs in our galaxy. But off to the left at the sort of sub-day timescales, there's this shoulder of additional lensing events that basically has to come from planets. And if you turn the sort of statistical crank of asking, given that we've detected this many events, what does that imply about the underlying population of free-floating planets? You get a sort of astounding number of 20 free-floating planets per star, albeit with healthy error bars. So this is still sort of in the regime of small number statistics. But it seems like there's a substantial population of free-floating planets. If that seems impossible, I should note that this population corresponds to about 80 Earth masses worth of planets per star, and something like 2 Neptunes. So they've done what you do when you don't have a lot of data, which is fit a power law to the observations you have, and the best fit power law gives you this population of planets. If you take the nominal best fit, based on the inference that they've done, you find that and project what Roman should detect, we should find a few thousand, maybe of order 1,000 detections of free-floating planets from Roman. Okay, so it's thought that, or generally understood, that star formation can really only make things down to masses of order, say, Jupiter mass or a little bit more. And so free-floating planets less massive than that basically have to form around stars and then be removed through some sort of dynamical phenomenon. And one way to readily do that is to have planets ejected from systems via planet-planet scattering. In fact, it's thought that our solar system might have even formed a free-floating planet early in its evolution. So this plot is taken from a study by Batigan from 2012, where they're simulating the early evolution of our outer solar system, and they've started the giant outer planets in an initially compact configuration and put in an extra ice giant planet. At the time the disk disperses, it's no longer there to sort of damp down the mutual perturbations that planets give each other gravitationally. They quickly develop an instability, become orbit crossing, and this extra ice giant crosses orbits with Jupiter and quickly gets ejected out of the system to become a free-floating planet. So one bit of dynamics that'll be good to have in mind going forward is the idea of the Safronov number, which determines what happens when planets undergo planet-planet scattering. And this number is a dimensionless number that is the ratio between the energy required to escape from a planet's surface relative to the energy required to get out of the star's potential well at that planet's orbital location. And so planets for which this number is much less than 1 are incapable of ejecting things because in order to transfer enough energy to whatever they're scattering, it requires a close encounter that is closer than the planet's radius, i.e. they're just going to crash into each other. Whereas if this number is greater than 1, then the planet is sort of geometrically small compared to its radius of gravitational influence, and it can readily remove stuff from the system. So I've put a couple of our own outer solar system planets on this plot, and they're sort of squarely in the regime where you expect them to kick things out. That's why Jupiter, in that last example, was able to readily kick out the extra ice giant, whereas our own terrestrial planets, including the Earth, are sort of squarely in the Safronov number much less than 1 regime. That's why we have a moon. Whatever protoplanet was scattering around the early solar system wasn't able to be ejected by Earth and instead crashed into us in the moon-forming impact. Okay. So one of the key features of Roman is that it's going to probe the regime of planets, or low-mass planets, in the regime where you expect them to eject planets from the system rather than collide with them. In other words, they're in the Safronov number greater than 1 regime. So I'm plotting this planet mass versus orbital separation plane again, and now I've added to the background a line where you expect the division between planets with a Safronov number greater than 1, shown in the yellowish color above the line, separated from the planets that are expected to collide with anything they scatter below the line. You'll notice the vast majority of things that we've detected to date sit below this line, whereas a healthy fraction of Roman's detections will be in this regime where they're kicking stuff out. This is even more significant when you consider the fact that the typical host star of planets is a fraction of a solar mass and not a solar mass star. So I'm making the same line again, but now for a third of a solar mass Imdorf. And so lots of Roman's detections should be in the regime where they're kicking stuff out. So I like to sort of summarize this pithily as saying that Roman will detect the stuff that's kicked out of planetary systems with free-floating planets and the stuff that did the kicking in its bound population. And so the name of the game is then to try to put those back together and figure out what happened in these systems. Okay, so I mentioned earlier that we already know from ground-based microlensing surveys, as well as radial velocity surveys, that our solar system is a little bit unusual in the fact that it has a Jupiter mass planet around it. That's a sort of 1 in 10 occurrence for solar-like stars, and the occurrence rate gets even lower when you consider lower mass stars. So that means that the sort of scattering dynamics that we saw where Jupiter made quick work of this extra ice giant will play out differently in systems when there's no giant planet to efficiently eject things.
Wait, is that 10% that's for cold Jupiters or Jupiters?
That's cold Jupiters. Hot Jupiters are a sort of negligible. I mean, that's like a 1% thing. So if you want to add them together, maybe 11%.
But then is that like, how are you doing that? Because like, is that a mass range, or you're saying above a certain mass, like half of all of them have a binary, right? So at what point, where do you draw that line in mass?
For what's a cold Jupiter?
No, just mass of when you're
Of mass, of the percentage of things that have a...
50% are in a binary system, right? So there is a massive thing companion. Then if you go down in mass, at some point you get 100%, right?
You're saying, stellar companion.
Yeah.
Companion, so what's the upper limit for that mass? Yeah. I mean, this is in some separation window as well. So different studies have adopted different things. The 10% from the microlensing thing, for example, comes from, they fit like a double Gaussian with a peak. They have a free parameter for,
Okay,
you know,
so the 10% is roughly in that circle.
yeah, the 10% is, it's roughly in that circle, yes. Different studies probably have slightly different cuts, but no matter how you slice it, you're going to get something that's like 10%. Okay, so like I said, we're sort of unusual in the fact that we have a Jupiter. The more typical system out there, based on what we know about planet occurrence rates, will be something that's predominantly made of Neptune-scale planets. And so what happens when you let the scattering dynamics I described earlier go in a system of low-mass planets? What you find is that low-mass systems can take a very long time to eject planets out of the system. So here I'm showing an example numerical simulation where I've taken a system of 5 Neptune planets, set up in a configuration initially on circular and quasi-planar orbits. They go unstable after a few million years and start orbit crossing. One of the Neptunes gets kicked in, absorbing most of the system's initial binding energy, while the other planets are cast out to hundreds or thousands of AU. And it's not until about 1 billion years that you completely eject the first planet in red. And even after 3 billion years, there's still 3 planets hanging around at large distances in the system. Okay, so that was one example. You find, if you run lots and lots of similar numerical integrations, that the timescale on which planetary systems dissolve as a result of mutual scatterings is a strongly mass-dependent function. So here I'm summarizing ensembles of 100 integrations, each all comprised of 5 planet systems, and each ensemble, all I've done is change the initial masses of the planets. So systems where all 5 planets are Neptune mass are shown by the black line there. So those are systems like the ones I showed in the previous example. And then the masses increase up to 30 Neptune masses, or something like a Jupiter and a half. And so in the high mass systems, what you find is that the scattering proceeds fairly quickly, such that after 10 or 100 million years, you're reduced down to a final state of 2 planets. And those 2 planets are universally, or almost universally, sort of dynamically decoupled from one another. So that's really where the system is going to end up. But in the lower mass systems, you find that you're left with, on average, 3 bound planets. This is 1 that's kicked in, absorbing the initial binding energy, and then 2 still hanging around in the outskirts of the system. Yes?
Can you say a little bit about the separation in terms of theory?
Yeah, so what I did, well, this is an opportunity to get on my little soapbox about Hill radii not being the right thing to use in mutual planet systems. I can tell you more about that afterwards. It should be mu to the 1/4, not mu to the 1/3 that you normalize separations by. But at any rate, I set them up in a way that they go unstable on, I think I chose like 10,000 to 100,000 orbits. They quickly forget their initial conditions after they enter the scattering phase. So it's really not going to change your conclusion unless it starts taking billions of years for them to go unstable, in which case it's just going to take even longer. Yep.
Was the purple recaptured? Like, why did it do that?
So it had, what did it do? It looks like it got some energy from the orange. It probably came too close to the orange one. You can see it's a little tricky to tease out on the log axis because you'll see tiny movements. Right, it takes a little bit of fractional change in things that are closer in to make a big change in things that are loosely bound. But you can see, I should have said what I'm plotting here in case it's not clear. The solid lines are the planet's semi-major axes, and then the shaded regions are the apocenter and pericenter distances. So the sort of colored bands are the basically the radial extent of each planet's orbit. Yes?
I'll bite. Why is it mu to the 1/4 rather than?
So it has to do with overlap of resonances among planets. This is sort of generically understood to be the source of chaos in any sort of conservative system. And if you work out like the degree of overlap in a multi-planet system, what happens is you get basically the widths of three-body resonances relative to the amount of space available for them to fill up phase space scales like their separation divided by mu to the 1/4. It's also true actually in two-planet systems as well. So you can have chaotic two-planet systems that are protected by Hill stability, for people who know what that is, at a certain mass range, because the threshold for chaos is different than the threshold for being able to have close encounters. And so, yeah. And then there's no such thing as Hill stability in multi-planet systems, and people have just been. In fact, one of the original works on this, Chambers 96, who did like empirical fits to numerical simulations, already showed empirically that mu to the 1/4 was a better fit, and people just ignored it or something. So I'm trying to get this out of the bloodstream of astrophysics. Okay, so what happens to these scattered planets? They're sort of generically found at separations of 10 to 100 times where they started out. So in this case, I started things at 10 AU, and you find them at 100 to 1,000. In this panel over here, I'm summarizing the cumulative distribution of the expected projected separations of planets that hang around at the end of the simulations, and all the different mass ensembles. So it doesn't seem to depend much on planet mass. I've excluded the inner planet that gets kicked in, absorbing all the binding energy. So these are all the outer scattered planets. And they're sort of uniform in log between about 100 and 1,000 AU in this case. You can scale that to their initial separation. OK, so we can conclude. We can put together what I've said so far, namely that Jupiters are rare, Neptunes are abundant, Neptunes take forever and are inefficient in scattering things all the way out, and instead sort of strand stuff at large distances, to conclude that a substantial fraction of free-floating planets should instead be what we call detached planets. So they're in the outer regions on highly eccentric, large semi-major axis orbits. And so it turns out that the microlensing method can only determine that a planet is bound if it's within typically 1 to 10 AU of the star. At these sorts of distances, these planets look basically just like a free-floating planet. OK, so what do you do about this? This is something you can actually test with follow-up observations and go after host stars of detached planets. And the idea is that if you see a lensing event, you can go and follow it up later, a few years later, or even better, if you have precursor observations a few years before the event, what you should see is that the background source star and the host star of the planet that did the lensing should separate on the sky to the degree that you should be able, in high contrast imaging, to determine if there was a host star, in fact, there. So when the lensing event happens, the flux is blended together and you can't really separate them. But after they have some time to move apart, you should be able to find that there was, in fact, a host star near where the lensing event occurred. OK, so far I've said that we can use free-floating planets to say something about what's going on in the outer regions of planetary systems that Roman will be probing, and say something about their dynamical evolution. And now I just want to conclude by turning to the implications of this sort of scattering dynamics for the entire system. So it turns out that this dynamics can have consequences not just for the planets in the outer regions, but also affect planets closer in. And then I'll also talk a little bit about our own solar system. So the reason that this can have consequences for planets closer in is because while planets are undergoing this scattering, you can excite very high eccentricities among the scattering planets, especially that planet that gets scattered in closer to the system. So in this example simulation, you see that the pericenter of this green planet occasionally drops to very low values off the scale here in this plot. And if you look, it turns out that low-mass planets especially are susceptible to very close pericenter passages. And so we know that lower mass planets are the most typical. And so that means that many of the systems that are out there doing the scattering can produce very close pericenter passages. So this plot is a cumulative distribution of the minimum pericenter distances achieved by a planet in the ensembles of simulations that I was describing earlier. And you can see that the Neptune mass planets, especially shown in black, get to very close pericenter distances. So you should be raising an eyebrow when you see the units at the bottom of this, because a solar radius sits about there on this plot. And that means that the scattering can readily just dump planets onto the star. I should say the simulations that I've been running are highly idealized. I haven't given anything any sort of physical extent. So this is up to now has been purely point mass dynamics. So what's the consequence of adding some physical scale to these simulations? Well, you find that you dump planets onto the star. So this is another simulation. Again, I'm putting, in this case, instead of Neptune planets around a solar mass star, I'm putting half Neptunes around a half solar mass star. So from pure point mass dynamics, it's exactly the same. But I've added the appropriate physical radii for everything now. And you see that the scattering starts out more or less the same. Everything gets kicked up. And then you excite very high eccentricities. And at a couple points, you dump planets onto the star. And as a consequence of this, you're sort of removing one of your sources of scattering for these planets that have been kicked out to further distances. So, when I was not removing them, they had the opportunity to scatter every time they swung through pericenter and came back and interacted with this inner planet. When you get rid of them, it's no longer there. And so the dynamics slows down even more, and you can really strand free-floating or these detached planets at large distances. They sort of still gently scattering each other, but they're basically stuck there for a very long time. Okay, so that was one example. If you run an ensemble like I was showing previously, you find that on average, you dump a couple planets onto the star, and you're left with 3 detached planets hanging out. So the picture doesn't change that much. You still expect to find detached planets. Now we've gotten rid of our source of scattering.
Wait, so it's more common to collide with the star than be ejected?
Yes, it was more common. Yeah, because you're removing that inner planet, right? The things that are scattered out, they're way out, and they'll basically never see each other. And so a lot of the scattering and the sort of chaotic diffusion of your semi-major axis is driven by your encounters with that planet that came in and absorbed most of the binding energy. And that's the one that you tend to dump onto the star.
And it's roughly like 10 or 20 times more.
Yes. Yeah, there was like one ejection in this ensemble. I think this was 20 integrations. So maybe there's some Poisson error bars, but
where are we in like the lifetime of the solar system in terms of planetary disk and a debris disk? Like the debris disk is usually on by
down here.
Wait, and even
yeah. So that's
interesting. It's all.
Yeah, things move slow because they're getting way out there. Yes.
So you haven't said much about the ensemble that you started with. Is this result sensitive to your assumed initial state for the planetary system?
The only thing you really need is for it to go unstable, and as long as it's not taking billions of years to go unstable, or if things never go unstable, then I guess they just sit there and never do anything interesting. But we know already that there's lots of free-floating planets, or potentially detached planets. So there's only a few ways to do that. One is to kick them out or make them detached. Another is to somehow manage to hide lots of planets that never go unstable beyond 10 AU and just keep them there so that you'd be blind to most of them. And then in which case your conclusion either way is that there's lots of planets at large distances beyond 10 AU. And the question is just, is it 1,000 AU or is it 50 to 100 AU? So yes, we are assuming that the planets sort of generically undergo scattering at some point, or undergo instability. And if planet formation is fairly efficient, then it's easy. You would imagine it's easy for a sort of protoplanetary disk to make lots of planets. It has no knowledge of how long things should dynamically last for. And if you make a system that's happy to be dynamically stable on the order of the time scale of the planetary disk, then nothing's really going to happen over the formation time scale, but on longer time scales, it goes unstable. Right. Okay, so on their way to crashing into the star, these outer planets can also impinge on any sort of intervening planets. Whoop. Oh no. Yeah, there we go. So I mentioned at the beginning of the talk that we found lots of planets close in. The sort of typical distance for the most common type of planet we know about, so-called sub-Neptunes, is 0.1 AU. So we find lots of planets there. We know these are sort of intrinsically common type of planet. And so if there's scattering going on in the outer regions of systems hosting these sorts of planets, it can have consequences for those inner systems. So here I'm showing a simulation run by Yikon Mao. He was an undergrad who worked with me on a summer project to look at what happens if you take an outer system showing the sort of scattering that I've been describing and stick inner planets in there as well. So he's initialized an inner system of 3 sub-Neptune planets, initially on very cold and boring orbits, where they're not doing anything too exciting. And then after a few tens of millions of years, the scattering dynamics that's taking place in the outer system sends in this inner planet that's absorbed most of the binding energy. It comes sort of whizzing through and excites some eccentricity in the inner systems, kicking up. So it's had an imprint on the dynamics of the inner system. And you even find cases where it can have a dramatic impact, namely, it can trigger orbital instabilities in the inner system. And so it kicks up eccentricities among that inner system, and they end up colliding with one another. Okay, one thing I should mention is so far I focused on equal mass planets scattering one another. If you look at what happens in the case of having one sort of dominant scatterer, and a bunch of smaller planets, you find that a more massive planet can sort of guard against this sending things onto highly eccentric orbits. So here is a simulation where I've put in 10 Neptunes in a single Jupiter mass planet. And what you find is that the Neptune, or rather the Jupiter, scatters out a large number of the Neptunes. But even in this case, with this many Neptunes, what you find is that you can get some stuck in the outer regions of the planetary system because while they're on their way being scattered out, they torque one another and can lift the pericenters, each other's pericenters, away from the Jupiter and be temporarily, at least, safe. And so if I let this play out even longer, eventually what you would probably find is that one of the pericenters would drop below and become orbit crossing with Jupiter. But again, that takes a very long time, so you can even have detached planets if you insist that Jupiters are really the things creating the vast majority of free-floating planets. Okay, so with the mention of the Jupiter example, that might lead you to ask, what about our solar system? We have a Jupiter. Did it save us from the scattering dynamics playing out in our outer solar system? And I mentioned earlier that people think that our giant planets underwent a dynamical instability, and a lot of the evidence for that comes from so-called trans-Neptunian objects. This is the population of small bodies that exist in our solar system beyond the orbit of Neptune. These are often divided in all sorts of different dynamical classes. There's a sort of cold belt-like structure that's sort of reminiscent of the asteroid belt that is called the Kuiper belt. But then in addition to that, there's lots of bodies on highly eccentric, large semi-major axis orbits that take them out to hundreds or even thousands of AU. And these things are really what are part of the evidence for dynamical instability in our outer solar system. And I should mention that in the near future, we'll be getting a lot more of these thanks to LSST. It'll be a great machine for finding things that move in the solar system. And so it's projected that we'll get something like an order of magnitude increase in the number of known TNOs. And so we'll have an even better sort of fossil record of what happened in the outer solar system. And so the basic sort of picture that's emerged for how we think the outer solar system evolved often goes under the name of the Nice model, named after an observatory in France where it was first proposed. And the basic idea is that the giant planets initially started out in a more compact configuration. Once the disk goes away, the more massive initial population of planetesimals starts scattering with the planets because the disk is no longer there to damp their orbits. This causes some orbital migration. This orbital migration of the planets eventually triggers an instability, scattering Uranus and Neptune, and possibly an additional ice giant or two out of the system. And it's these interactions with Uranus and Neptune that implants the planetesimals on their present-day orbits that we observe among the TNO population. And in fact, we see the sort of leftovers of these scattered planetesimals in what's called the scattered disk. So these are shown, illustrated in this plot here from a paper I did in 2024. There's a lot of lines on this plot. You don't have to pay attention to them all. What's important here is basically this orange line that separates points or separates regions of parameter space where things actively scatter off of Neptune and evolve in semi-major axis in a sort of quasi-random walk way, whereas things above the line are basically frozen at their current location. And you can calculate that the removal timescale for things with a pericenter distance greater than about 35 is on the order of gigayears. So it's unsurprising that we have a few of these sort of things hanging around. And if you look, the vast majority of things at large semi-major axes can be explained by just their long-term evolution scattering off of Neptune. However, what's very difficult to explain in sort of conventional models of this instability are objects that are in this regime where are not expected to dynamically interact with Neptune. So there's sort of some in this swath up here that are removed, but then there's these very extreme objects, sometimes referred to as sednoids, on very large semi-major axis orbits with pericenters completely removed from any interaction with the giant planets. Probably the first thing you learn about gravity is what goes up must come down. That's true in this case as well. So things that get kicked by Neptune have to come back to pericenter, basically where they got kicked by Neptune. So there's no way for them to just get stuck at these very large pericenter distances without any sort of extrinsic dynamical interactions with something else. And so I've been talking this whole time about scattering out planets on very long timescales and leading to either detached planets or eventually free-floating planets. And one potential mechanism for putting the sednoids on their current orbits is to have a planet sort of slowly get kicked out by Neptune over the evolution of the solar system, say for the first 100 million years or so. So this is a simulation by Yukon Huang and collaborators sort of illustrating how this mechanism works. They've put a 2 Earth mass planet on this orbit here, the pericenter distance at 40 AU, semi-major axis at 300, and they've initialized a sort of proto-scattered disk. So this is the sort of distribution of orbits you would expect just from Neptune scattering among planetesimals. And I'll go ahead and press go. And what you find is that while the planetesimals continue to scatter in semi-major axis due to their interactions with Neptune, what happens is that torques from this rogue planet are able to lift a lot of pericenters of these bodies out of contact with Neptune. And so in this particular initial conditions, this rogue is sort of safe from Neptune, but the idea is you have long-term scattering off of Neptune, so this thing hangs around for a while, is able to torque things out of the way, and then eventually gets kicked all the way out to become a free-floating planet, just like we've been talking about this whole time. Okay, So that brings me to my conclusions. So I told you that microlensing lets us probe planetary systems at distances similar to our own solar system planets around other stars, a parameter space that we've been largely blind to till now, and that we can use the bound and free-floating planet populations discovered by microlensing to link back together how these populations have been shaped by scattering dynamics. I told you that many of the apparent free-floating planets should be weakly bound, since we know that the scattering dynamics should more often than not be driven by low-mass planets. And I showed how the scattering dynamics can have consequences for the entire system and how it might have played out in our own solar system as well. So that's it.
Okay, questions? I guess my intuition is still failing in terms of like the dynamics of kicking things out or dropping them into the planet. It really seems like, I know you've done the math, that it should happen early on, and instead of like after 100 million or 1 billion years. Why
does it take so long?
Yeah, why does it take so long? Is it you need a lot of crossings, but
Yeah, you just need lots of encounters to get you out. So you're really in the sort of diffusive regime where your transport is dominated by lots of small kicks instead of one big kick.
But in the early era of the solar system with like the debris disk or the planetary disk, you have lots of those, right? It's like
Lots of,
potential scattering events.
but with lots of low mass stuff. Yeah, there's not a lot of things to scatter.
Okay, so it's more like a drag than a.
Yeah, I mean, so if you have lots and lots of little stuff, then if you're a big thing, you'll get a sort of dynamical friction effect as well.
That's it. Okay.
But that's, yeah.
You talked about how microlensing gives you a point estimate, a one-time thing, and then eventually you can observe the system and learn more. Can we combine that with radial velocity or transit method, for example? Because these are larger planets.
Can you follow up microlensing detections with other? Almost universally not, because you're really probing things at orbital separations where the signal is just too weak to ever. Yeah, I mean, they'll almost never transit because the geometric probability of getting a transit for any of these is minuscule. And yeah, for radial velocity, even in the relatively rare case where you find a giant planet, more often than not, it'll be around there's lots more faint stars than bright stars. So you'd have to get really, really lucky to find a bright star that was amenable to radial velocity observations that also happen to microlens.
Thanks.
I have a question. So I think you made a clear prediction that of those 1,000 new microlensing events that Roman is going to see, that almost all of them will be detached planets.
Yeah, or I would, yeah. So we make a crude estimate in the paper of something like half.
Something like that.
Yeah, so about half.
Okay.
It's sort of a back of the envelope based on the fact that, if you tend to retain about 2 Neptunes and kick the other ones out, and if you add up all the Neptunes you need, yeah.
Okay, so the question is, what would you say if it turned out that 90% of them were unbound and only 10% were detached? Where would you go to?
If most of them were unbound, that would be a head scratcher. I mean, one way to sort of get them all the way out is in the birth environment when there's stars flying around. And people have talked about this before, but the problem with that is that you need to get the planets out to where they would be susceptible to being sort of stripped off by a stellar flyby on a timescale of the birth cluster's age, and that's not really doable with Neptune-mass planets. The clusters usually dissolve before, like the cluster timescales are 1 or 10 megayears, and the time scale to transport things out is usually too long. So that would, I think, you would have to really, that would be a surprise. I would, if there's just not that many free-floating planets, I would say, you know, like I said, this ground-based estimate is small number statistics still. You saw the healthy error bars. So it could be that dynamical friction from planetesimals sort of shuts this process off before it gets carried away too far. But yeah, that's the main thing I envision sort of breaking this story.
Seems like a real hard problem to disentangle the microlensing signal from free-floating planets from regular stellar variability, right? Because you don't have the kind of correlated double peak. How can you say something about how
Yeah, I mean, there's certainly people who think about like microlensing models a lot more than me, but I mean, you do predict a sort of characteristic shape that comes from microlensing. You know, you can write down, it has somebody's name attached to it, but it's this sort of characteristic curve. And so the way you would approach that is to do some sort of model selection thing where you fit it with your best fit microlensing model and compare that against some model for variability and see what the Bayesian evidence says, or pick your favorite statistical test.
Yeah. I guess for every star, you have a long baseline of variability already.
Yeah, right. And yeah, so you also will have, you know, these
Statistic
continuous observations from Roman to see, you know, if it's continuously doing funny variable stuff, then it's probably not microlensing.
Okay, let's thank Sam.